science, technology, engineering, and mathematics, easy to comprehend, assimilate, fun, and entertaining. Please, if you have not subscribed, kindly subscribe and assist in making it go viral. Letting others enjoy this is also good for us. Those are the motivations that encourage to continue the class. We are on permutation, combination, and probability. We have treated permutation and combination, and today we are treating probability. Probability or chance is a measure of the likelihood of an event happening or not happening. What do we mean? It is about assurance, about certainty of an event happening or not. Sometimes you might not be so sure, and sometimes you might be fully certain that this event is going to happen. And that is what probability is talking about. Probability is a kind of expectation, and sometimes it might be nil. Sometimes it will never happen. Sometimes it might be it will surely happen. Sometimes it might be dependent on one event happening for this one to happen. And that is why probability is always between 0 and 1. 0 and 1. When it is 0, it means it will not happen or it cannot happen. When it is 1, it means it will surely happen. It will surely happen. So, and from here, we have its fraction, 0.2 this point. And sometimes you might express it as a percentage as well, depending. But most times it's expressed in fraction. Now, why? Because it is about comparing the events happening to general, outcomes. Let's continue with the terminologies. Random, it means without aim or chance in an unbiased ways. When we are talking about random, you want to select something, you want to throw dice, you want to flip coin. It's random. We are looking at it with the mindset that you are not tampering with the results to happen. You are not going to do something behind the scene to make certain results to happen. Like, you have just done it and you have thrown it to chance. That is what we mean by random. Like if I pick a coin and I throw it, I have not tried to attach something around it so that when it drops, it's going to give me a certain result. To the dice, I have not done anything around the corner of the die to make sure that it falls on one place. That is what we mean by random. Or if I have put some people in a classroom and I've not whispered to someone that when I say somebody come, I say I want to pick somebody. Somebody should stretch his hand for me to pick. That is, I have already made sure that that person will be my results. No. It's just like you blindfold yourself and then you pick. That is what we mean by random. Event means something happens. Something that happens. That is, we aim for when I call, the students come, who do I pick? It means like certain amounts will flow into my hand, or certain money will drop. Those are the things that we mean by events. Outcome, result of an event. That is, when this event happens, what are the kind of results we have? Just like when you throw coin, when you flip coin, you are going to have head or tail. So those are the outcomes. When you throw dice, you are going to have results or outcome of 1, 2, 3, 4, 5, 6. You can never have 7 and you cannot have 0. So that is it. And if it is a pack of cards, you might have ace, you might have jack, you might have king, you might have queen, you might have one. You cannot have 1, but you can have a. Depending on the kind of card you play. But this kind of card that we always use is between A and 10. And then we have red, hearts, and what's it called? And we also have these other ones, depending. So those are the things to talk about results. Sample space, set of possible outcomes. That's what I've just said. Sample space, that's set of possible outcomes. They are the result of this. They are the same thing with this. When outcome is the required result, it is referred to as successful or favorable. Now, if I have desired that once I throw this die, I should have 2. When you are playing Ludo, there are sometimes that the only number you need might be 2 to win the game. So, if you throw it now and you have 2, that means that you have succeeded. You have succeeded. But if you have something else apart from 2, you have not succeeded. You still be doing the trials further and further. So that's what we mean by successful or favorable. So probability now means that, okay, when we do these trials, most times, when we do 6 times, we can have these 2 once out of 6 times. So that is what we mean by probability. This number of successful outcomes and total number of possible outcomes, these are trials depending on how the game is arranged. experimental. Okay, so in terms of experimental this thing, we talk about trials. That is probability based on experiments, which gives relative frequency. And relative probability is frequency of the desired event over total number of trials. That is it. Sometimes it might be trials. Sometimes it might be total outcome. Like when we are talking about dice, we have already known that okay, since these are non-biased dice, the probability of getting 1 and 6 they are the same thing. 2, 3, 4, 5 they are the same thing. So the probability is 1 over 6. So that is what I want. I want us to have that, foundation before we go on. So I will give you more as I proceed. Now, let's talk about some other things. Relative probability or frequency is expectation over total number of trials. So what are we trying to say? That if we know the probability or frequency of an event to happen due to historical experiments carried out or whatever, I want to think of what the expectation will be. We will need to just use this equation. If you want to calculate the expectation, we can just say probability multiplied by trial will give us the expectation. That is about that. Now, when we are talking about theoretical probability, in most cases, this one is something like, this is our own belief. I don't want to use the word assumption. This is our own belief that this material we are using is unbiased. For me, even this divination and whatever is about this relative frequency and expectation. Let me go back to that. Probability generally. But, well, they said it is about divine, probability in the divine. Let me use that word for divination. Now, theoretical probability. Let's concentrate on this now. Probability of an event based on equally likely events is called theoretical probability. That is, you just look at it and say, okay, based on this as it appears, everything, the probability of this one happening is this. The probability of this one happening is this. Like when you look at a dice, you just say, okay, fine. See, there is nothing special about one place to the other. The weight of one place is not bigger than the other. Everything is the same. Once I throw it, there is nothing that makes one place likely to happen than the other. So you can easily say, okay, theoretically, the probability of one place showing is 1 over 6 because it has 6 sides. A coin, it has 2 sides. So, and you have not done anything special to one place that will make one place to drop or to turn up. So that's why we talk about theoretical probability. Mainly, whatever we are going to do is still going to be on theory, on calculation. But the genesis is what we are talking about. What prompts our results? One is mainly experimental, the other is theoretical. Experimental means various trials have been carried out, and based on that trial, they have decided that, oh, the frequency of an event happening is this. Like, if you have 100 trials, 100 trials of, shooting, and at the end of the day, 60 is on target. It means that the probability of targeting will be 60 over 100. That is 0.6. You understand? This is based on experimental. He had done it. He had experimented it. So, which means that if I want to bet on him or do anything on him, I know what my risk is. That is what we are saying. But in theoretical, there's nothing special about it. You don't need any special skill to throw a dice, to throw a coin. That's the assumption, and that is for theoretical. Now, probability of an event happening or not happening. I'm just trying to develop this foundation. If probability of an event happening is E, the probability of an event not happening is E, E complement, like we do like this, is equal to 1 minus E. 1 minus E, that is, it is happening. So which means that E complement plus E is equal to 1. So that's what we mean. Okay, let's talk about combined probabilities now. In other combined probabilities, we have mutually exclusive, independent, non-mutually exclusive, and dependent probabilities. Let's go into those ones. Now, let's talk about combined probabilities. Here we have first one, mutually exclusive events. If the occurrence of one event prevents another one to happen, how does that happen? Like, if I go out now, I cannot be inside the house again. So that is mutually exclusive. I cannot be outside the house and inside at the same time. And let's look at it now. If I flip a coin, and I throw it, I flip it, I cannot have head. Once I have head, it means I cannot have the tail. If I throw a dice, once I have one number, I cannot have the other numbers. So that is mutually exclusive. That is like this. If I have head, I cannot have tail at the same time. You see, so they are mutually exclusive. They are disjoint. Disjoint. So that is about mutually exclusive events. It means that when one happens, the other ones cannot happen. So that is mutually exclusive. For independence, here it says two events A and B are independent if the outcome of A does not affect the outcome of B. Now, let's look at the situation where I want to find the probability of picking a ball from a sack. I have white 6, black 4. You know, if I pick one out of this, the probability of having white will be 6/10. You can see. Now, I want to pick another ball, but I returned the first ball back into it. I returned the first ball back into the bag, and I want to pick another ball. The probability of having black now will be equal to 4/10. Get it now? That is, the events of what I did in the first time did not affect the probability of the second time. Why? If I had picked, in the first instance, the probability of picking black is equal to 4/10. If it is the first one, the probability of picking. Now, if I return the ball back, the probability of picking black again is still 4/10. Same with white. So these are independent because I have returned the ball. It has not affected the outcome again. But if I not return the ball, it affects the outcome. So we get to that. That's why we talk about independence. So it is not affecting. Do you understand? So it does not affect the outcome of the other one. That is what we mean by independent events. Now, before I go on, in mutually exclusive events, if probability of A is P, the probability of B is PB. You understand? The probability of A or B, this addition is for A or B, will be equal to PA plus PB. PA or PB. Just like in sets. If here I have A, if here I have B, and they have to find P union B. This one has 4, this one has 5. So PA union B, or let me say N, total number. A union B will be equal to 4 plus 5. We can easily do that. The number of elements in A union B will be 4 plus 5. Why? There is no intersection. So it is disjoint. That's why this one can happen here. Exactly. But for independence, we can easily do what? Multiplication. Because PA and B will be equal to PA times PB. Conveniently, that is it. So you can easily find this out by using tree diagram or this outcome table. By the time you look at all this, all the results you get, you will find this out easily. So for independent events, it is PA and B is equal to PA times PB. Get that? For mutually exclusive events, PA plus B is equal to PA plus PB. If they are not, there are the other ways of calculation. Now here, we are talking about non-mutually exclusive events. Unlike in mutually exclusive events, if one occurs, it prevents another one to happen. So here, we are going to have something like this. It means that we have a situation like this. That is, when this happens, it affects another one from happening. Let's call this one A, let's call this one B. And the full total here now. This place now is A minus N, B minus N. You can see. So we might have another thing here, but we are talking about the addition of A and B. So if I want to add A and B, I'm going to have A minus N plus N plus B minus N, which is equal to A plus B minus N. So what does that imply? It implies that for non-mutually exclusive events, the addition PA plus B will be equal to PA plus PB minus PAB. A and B happening together. That is what the non-mutually exclusive events, that's how we add the non-mutually exclusive event side. That is all. Now let's look at dependence. The format of calculation in dependence and independence is very close. It's just for you to recognize that some are dependent, some are not dependent, some are independent. That is all about dependent. I'll write that one now. So I hope you have gotten this now. This one is for non-mutually exclusive, when there is interaction between the two. Here it is mutually exclusive. See the difference now. Now let's look at dependence. Now, dependent events, when probability of one outcome affects the other, we say the events are dependent. In this event, the probability of an event is dependent on the previous event. Most times, that's why we talk about dependent events. Like I used the other time, I talk about when we have 6 white balls and 4 black balls. And the probability of picking white ball is 6/10. Now, if I pick this, I do not return it inside this, the box. And I want to pick another one. The probability of having white this time around is equal to 5/9. Because the white has reduced by 1 and the total quantity of balls has reduced by 1. So, the probability here of having black will be equal to 4/9. This is the second selection. Now, assuming the first one is black, it's going to be 4/10. And for the second selection, P white will be equal to 6/9. P black, probability of black will be 3/9. So you can see. So in this instance, this one is dependent on this one happening. So for me to be able to say, okay, what will happen in the second instance? I must have said, okay, if this happens in the first instance, this is what can happen in the second instance. I cannot just go straight to the second instance. But had it been, I have returned the ball back into the bag or sack or box. I don't need to consider this part to be able to decide the possible results of this end. That's what we talk about dependent events. And just like independent events, we can also say that PW, that is the two of them happening together, is equal to PW times PW. That is, this will be dependent on if W happens first. That is what this result is talking about. Talk about the relative frequency of this one. So that is how we get that of the dependent events. Let's look into some things. Now, when we want to work our probability, there are some things that we might come to use. Sometimes we might use outcome table. Like, if you want to have something like, okay, tail and any number of the dice, or tail and tail, if you throw 2 dice, so you can use outcome table. Let's look at what I mean. Like this. So if you are going to throw 2 dice, so you have TH, TH. So you can say TT, TH, HT, HH. So you might use this one to say, okay, what is the probability of having head and head? We have 4 possible outcomes here. So I can say, okay, P head will be equal to, when I throw 2 dice, it's going to be 1/4, because this is 1/4. So that is one tool you can use. Another tool you can use is tree diagram. Now, head, tail, let me use this. I'm just using an example. When you go into real workings, you can. Now, permutation and combination. And again, it might result into binomial expansion. Binomial expansion. So, depending on, it's not fixed that you must use one kind of workings, but one might make it getting the results very easy and fast. That is why we explore all these techniques in working out our answers. Now, let's look at some examples to illustrate what we have been studying. A bar contains 3 red and 2 yellow discs only. When a disc is drawn from the bag, it is returned before the next draw. What is the probability that the draws will yield both discs the same color? We've discussed the tools you can use to analyze probability, like tree diagram, space diagram, and permutation combination. Now let's start with just drawing the sample space diagram. Here we illustrate all the possible outcomes that we can have. Here we have 3 red and 2 yellows. Now, so red, yellow, red, yellow. I know what makes it so easy for us to do this, because it is being returned. So one, it is independent. Independent. You understand? Independent events. And by the time you look at it again, it is mutually exclusive. Mutually exclusive. So we can easily make them look, and we can do it in a very simple and easy way, joyful way. Now look at this one. We are going to have RR, 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 RY, RY. Same thing here. Here we have YR, YY, YR, YY. And we asked, what is the probability of having the same color in the 2 draws? What is the probability that the draws will use both the same color? And what are the same colors we have? Let's check. They have RR. That is, the first one is the same color as the second one. So, if the first and second are red, how many trials will yield that? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9. If the first and second are yellow, what do we have? We have 1, 2, 3, 4. So we have 4. So what is the total possible outcome? Total possible outcome is equal to 25. So the probability of same color to be equal to 9 plus 4 over 25, which is 13 over 25. You can see that. So here we are talking about using sample space diagram. Let's look at it using another perspective as discussed. Now let's use the multiplication law now. The first one, be red. First and second, red. And don't forget, we have said they are independent. So what is the probability for the first one to be red? That is 3 over 5. What is the probability of the second one to be red? That is 3 over 5, because it doesn't change. Now, let's look at first and second being yellow. the probability of the first one being yellow will be 2 over 5. The probability of the second one being yellow is 2 over 5. Now, the probability of the first and second being red will be equal to 3 over 5 times 3 over 5. The probability of the second one being yellow will be 2 over 5 times 2 over 5. So, we have said the probability of the first and second being red will be 3 over 5 times 3 over 5. The probability of the first and second being yellow is 2 over 5 times 2 over 5. So here we have 9 over 25 and 9 and 4 over 25. The probability, we have gotten this now. So, using multiplication law and mutually exclusive, we can easily add this together. So the probability of being same color will be equal to 9 over, oh, this is 25 please. 9 over 25 plus 4 over 25, and that is 13 over 25. See, so it makes the job very easy. Another way to look at it, I show now. Now let's look at another way of looking at it using tree diagram. For this one, we have here red, here yellow, here red, here yellow, here red, here yellow. So it will still be tantamount to the multiplication law, but I want us to see so that we learn how to use the what's it called? Tree. Here we have RR, we have RY, YR, RY, no, YY, sorry. So when we have RR, what is the probability of having R? Since it is independent, we have this one to be 3 over 5, and this one to be 2, Y to be 2 over 5. So RR is 9 over 25. RY is not part of what we are looking for. YR is not what we are looking for. YY again is 4 over 25. So you can see how it goes. You can use this tree diagram for independent and dependent events. So probability for same color is equal to 9 over 25 plus 4 over 25, which is 13 over 25. Let's look at another way of handling this. Let's look at it from permutation perspective. Permutation perspective or arrangements. You know, in this instance, we can see that we can repeat. That is, you can return it and you can pick again. So in this instance, we have repetition. So total possible event is going to be 5 raised to the power 2. That is the total possible arrangements. That's total possible arrangements. Now, for us to have same color, it means that the first and second must give us same color. Now, what is the choices now? We have 2 choices to make. So which means that the first one can be red and the second one can be red in this instance. So, what is the available number of choices for us for the first one? For red, we have 3. It is returned. What is the, 3R, 2Y? It is now returned. What is the number of red possible in the second choice? We have 3. So the possible arrangements for red and red will be 9, 3 times 3. Now, if it is yellow, we are going to do the same thing. We pick one yellow first, and that means we have 2 choices to make. Opportunity to get yellow. So we have 2. We return that one. Again, we check, we jog it, and we pick another one. Possibility of picking yellow again is 2 for this place. So we have 2. So which is 4. So total possible arrangements for same color is going to be 13. Therefore, probability for same color will be equal to 9 plus, we have already had it, it's going to be 13 over total possible arrangements, that's 25. So you can see, you can view it from different perspectives and you will get your answer. Let's see, I will still do more, but with this, I think I have bring clarity to what you have been discussing. So, I will still do more exercises or examples. So to brighten our understanding or this permutation, combination, and probability. Thank you very much. Kindly subscribe, share, and thank you for all your support and motivation. Any question you have, please kindly throw it into the comment section or through the channels in the description. Thank you very much.